In this video, we're going to be looking at elevator problems. An elevator problem is a scenario in which we have an object that is being pulled up or being allowed to fall down, typically under some form of acceleration. If we have a scenario, let's say there is an object that is 5 kilograms in mass, and it is lifted with a force of, let's say, 15, no, let's jump it up to 100 newtons. Determine the acceleration of the object. So we're going to start off by drawing a free body diagram. Here's our object. It has an upward force of, we call that the applied force, which we know is 100 newtons. And then we have a downward force. That downward force is the force of gravity. The equation for the force of gravity is it is equal to m times g. G being the acceleration due to gravity of 9.8 meters per second squared. All objects, when they're in free fall, accelerate at this rate. So that is the acceleration caused by gravity, and because we know that force equals mass times acceleration, if we know that that acceleration is g, we can figure out the force of gravity. Now we can set up a net force equation. The net forces acting on this system, I'm going to say that they are equal to mass times acceleration, because all net forces equal mass times acceleration. That's an equation. Well, the sum of all forces over here is equal to the upward force, F applied, minus the downward force, Fg. So we have Ma equals 100 newtons minus, and I can substitute in our equation for mg there, mg, Ma equals 100 newtons minus 5 kilograms times 9.8 meters per second squared. And then I can divide this whole scenario by m of 5 kilograms, and I get A equals 100 newtons minus 5 kilograms times 9.8 meters per second squared, all divided by 5 kilograms. When I plug that in my calculator, I'll get a number along the lines of 11-ish, 100 minus 5 times 9.8 divided by 5, nope, not 11-ish, 10-ish, equals 10.2 meters per second squared. So the object is accelerating at 10.2 meters per second squared. This was just an object that was being lifted by an applied force. The big difference between that and an elevator is inside of an elevator we have a surface. So if I were to figure out the forces acting on this person, here's my free body diagram for the person, they have gravity pulling them down, but this surface would be pushing up on them. So we would have our normal force. The normal force is not just the force of the surface, it is also what we call the apparent weight. That's how much your weight appears to be. If Fn is greater than Fg, you feel heavier. If Fn is less than Fg, you feel lighter. So let's look at a couple scenarios. We have an accelerating elevator and it's accelerating down. The elevator is accelerating down at, let's say, 1 meter per second squared. So this would be if you got in an elevator on the top floor and you pressed the button to go down to the first floor. You go from having a velocity of 0 to a velocity that is down. If the velocity is changing, then we have an acceleration down. So we have our net force. Let's look at a free body diagram. We have Fn and we have Fg. If my acceleration is down, it tells me Fg is bigger than Fn. Equals ma equals Fn minus Fg. To get Fn all by itself, I would do ma equals, actually, you know what? I'm going to scratch that. I forgot to say something. Positive is the direction of acceleration. Whatever direction the object is accelerating, we're going to say is positive. That's just going to help us understand this a little bit better. Sum of all forces equals ma. If we're accelerating down, then down is positive. So my Fg is going to be my positive force. If Fg is positive, then Fn is negative. Okay. I want to get Fn by itself, but it's a negative. I don't like working with negatives, so I'm going to add Fn to both sides. And I get Fn plus ma equals Fg. I can subtract ma from both sides. And I get the normal force, or the apparent weight, equals the actual weight minus ma. So when I get in an elevator and I accelerate down, for a moment I will feel lighter than I actually am. The same happens when you're on a roller coaster and you get to the top of the peak. You start accelerating down. That acceleration down makes you feel like you weigh less. If that downward acceleration is actually equal to 9.8, so if Fn equals mg minus ma, if that downward acceleration is 9.8, the same rate as acceleration due to gravity, then the Fn would be 0, because we've got mg minus what would be mg. If Fn is 0, you're essentially weightless. That's when you get lifted up off of your seat. Ideally, if your elevator's working right, then you would never have that. Let's also look at an elevator accelerating up. Here we have, let's draw our forces, Fn, Fg. If it's accelerating upwards, then Fn would have to be greater than Fg. So Fn would be the greater force. Ma, again, A is the direction of our positive sign. So what force is in the same direction? Fn minus the force in the opposite direction is Fg. If I want to get Fn by itself, Ma plus Fg equals Fn. So here we have our apparent weight is actually going to be greater than our regular weight by this factor here. When you get in an elevator and you press the button to go to a top floor, you will for a moment accelerate upwards, and during that moment you will actually feel like you're heavier. There's also a middle regime. So after you get in an elevator and you decide to go up to the top floor, you're not going to accelerate the entire way. You're actually going to stop accelerating. When you stop accelerating and you start moving at a constant velocity, that is when our Fn and our Fg are equal. Here, the acceleration goes to 0 because of constant velocity. If the velocity stays the same, then it is not an accelerating system. We would call this a system in dynamic equilibrium. Dynamic means it's moving. V is not equal to 0. And equilibrium means that the net force, my handwriting is terrible right now, is equal to 0 newtons. We can also have static equilibrium. This is when the velocity is equal to 0 and the net force equals 0. We just have to remember that when net force is 0, all that means is acceleration is 0. It could be moving or it could be stationary. Those are two statements, again, of Newton's first law. An object in motion will stay in motion. An object at rest will stay at rest unless acted upon by an unbalanced force. So this should be enough to get you started on elevator problems. We will work more on them later.